November 7, 1943, Carpic Airfield, KH, France. The harsh headwinds sweeping across the English Channel had consumed fuel at a disturbing rate. Second Lieutenant William E. Roach of the 358th Fighter Squadron, 355th Fighter Group, watched his gauges sink toward empty as his Pratt Whitney R-2800 engine began to stutter. He faced an unthinkable dilemma. Ahead lay the safety of England, temptingly near yet impossibly distant given his fuel situation. Below stretched a patchwork of French countryside, some areas friendly, most still occupied by German troops. One airfield appeared strikingly similar to the Allied bases he knew well. Roach committed to his descent. The massive Republic P-47 Thunderbolt, serial number 42222490 and nicknamed Beetle, touched down gracefully on the grass strip. Roach followed a ground vehicle to a parking space, shut down his engine, and only then noticed the black Balkenkreuz painted on nearby aircraft. The Germans he had been battling minutes earlier now surrounded his cockpit with rifles leveled. Lieutenant Roach's combat flying career was over. He would spend the rest of the war in Stalag Luftwaffe, but the education of the German Luftwaffe was just about to begin in ways neither side could have imagined. What the Germans uncovered upon inspecting Beetle would reshape their understanding of American industrial capacity and technological sophistication. The P-47 Thunderbolt symbolized not merely a fighter plane, but a complete embodiment of American engineering philosophy, mass production, and material abundance. Over the next 18 months, as German engineers carefully disassembled, tested, and flew captured Thunderbolts, they confronted a sobering reality. Germany had not merely fallen behind in technology, they had been competing in a different dimension of industrial warfare altogether. The story of captured P-47s in German hands illustrates how overwhelming material superiority, when effectively applied to military aviation, could render tactical skill and pilot expertise insufficient to alter the war's outcome. The Thunderbolt would teach German engineers lessons they badly needed, yet could never implement. Their nation lacked the resources, factory network, and time to apply what American industry produced as routine output. The capture of Roach's P-47 on November 7, 1943, was not the first time the Luftwaffe had encountered the Thunderbolt in combat. German pilots had been engaging the bulky American fighter since April 1943. When the 4th Fighter Group first escorted B-17 bombers into hostile skies over occupied Europe. Early Luftwaffe combat reports expressed a mix of disdain and confusion. German airmen accustomed to the agile Focke-Wulf Fw 190 and Messerschmitt Bf 109 viewed the American machine as enormous, sluggish at low altitudes, and seemingly designed by engineers who ignored the realities of aerial combat as the Luftwaffe understood them. Reports from German fighter units through the spring and summer of 1943 repeatedly criticized the P-47's poor climb rate, its heavy handling at low levels, and what they saw as American hesitation to engage in traditional turning dogfights. The general belief among seasoned Luftwaffe pilots was that the Thunderbolt represented an inferior airframe that could be outmaneuvered at medium altitudes, where most battles occurred. That judgment would prove fatally incomplete. Yet, hidden within those same reports were clues suggesting a more unsettling truth that contradicted the myth of American inferiority. Pilots noted that Thunderbolts choosing to break off from combat could not be caught once they entered a dive. They mentioned 8 heavy Browning machine guns delivering devastating firepower when the Americans did engage. They remarked on armor plating that seemed immune to 7.92 mm bullets and often resisted even 20 mm cannon fire. Most disturbingly, they described how severely damaged Thunderbolts still managed to fly, limping home to England with battle damage that would have destroyed any German fighter. P-47s often returned to base missing sections of wings, engines leaking oil or shot-out control surfaces, yet remained under pilot control. When Lieutenant Roach's intact Thunderbolt rolled to a stop at Karpik, the Luftwaffe finally had the chance to inspect up close the aircraft they had been underestimating. Local Luftwaffe officers immediately understood the intelligence value of seizing a complete, undamaged American fighter. Within hours, Beetle was secured by armed guards to prevent sabotage. American markings were swiftly replaced with German Balkenkreuz insignia on the wings and fuselage, and bright yellow paint was applied to the undersides and tail surfaces. Standard Luftwaffe procedure, RLM-04 yellow, for captured aircraft to avoid friendly fire from German flak units. Soon after, arrangements were made to transfer the aircraft to Rechlin, the Luftwaffe's premier test and evaluation facility, located roughly 100 kilometers northwest of Berlin in Mecklenburg. The aircraft received the designation T9 plus FK, the code used by the Circus Rosarius Evaluation Unit. Hans-Werner Lerche, the principal test pilot and chief engineer at Erprobungsstelle Rechlin, was assigned to perform the initial flight evaluations. Lerche, who would eventually fly over 125 aircraft types during the war without ever crashing or seriously damaging one, approached the P-47 with professional curiosity and cautious respect. Given its unfamiliar systems, his first impressions, recorded in his flight log and later published in his memoir, Luftwaffe Test Pilot. Flying captured Allied aircraft of World War II reflected surprise at the cockpit's complexity. The instrument panel contained what seemed like twice the number of gauges found in German fighters. Strange levers controlled systems Lears had never encountered in German designs. The turbo-supercharger system required understanding of exhaust flow management principles that were theoretical in German aviation circles but apparently standard practice in American designs. The constant speed propeller operated differently from German equivalents. Most confusing was the elaborate system of automatic engine management that German pilots handled manually through constant throttle and mixture adjustments. Lears wrote in his memoirs, "The P-47 cockpit could baffle even an experienced pilot. I gradually managed to ascertain the function of most of the levers and instruments, but there were also some obscure controls, the meaning of which was not immediately clear to me." He spent considerable time on the ground experimenting with controls and studying the layout before attempting flight, a testament to his methodical approach to test flying unfamiliar aircraft without benefit of pilots, manuals, or operational documentation. The engine start sequence alone revealed sophistication beyond standard German. Practice, the Pratt Whitney R-2800 double. WASP required specific procedures to properly initialize the massive turbo-supercharger system. Lears followed the process methodically, his engineer's mind cataloging each step and inferring the purpose of each action. When the 18-cylinder radial engine roared to life, it produced a sound utterly different from the sharp bark of German inline engines, or even the BMW 81 radial that powered the FW-190. This was a deep, powerful rumble that spoke of enormous displacement and tremendous power reserves held in check. Leia taxied carefully, feeling the weight of the aircraft through the controls. The P-47D weighed nearly 10,000 Laderb empty, and this example was still carrying substantial fuel and full ammunition load, bringing it closer to 13,500. For comparison, the FW-190A8, one of Germany's heaviest single-seat fighters, weighed approximately 7,650 Laderb empty and roughly 10,800 Laderb at maximum loaded weight. The Thunderbolt was genuinely massive for a single-seat fighter, larger than some twin-engine aircraft in Luftwaffe service. Lercher advanced the throttle for takeoff, and the difference between German and American engineering philosophy became immediately apparent. The R-280 developed 2,000 horsepower at standard boost settings, with war emergency power reaching 2,300 horsepower when using water methanol injection. Germany's BMW 8001D, the finest radial engine in German production, and the power plant of the FW190, produced between 1,300 and 1,330 horsepower at maximum continuous power settings. Even with this power advantage, the P-47's greater weight meant the takeoff run was longer than Lurcia expected, consuming nearly the entire grass field at the transfer airfield. But once airborne, Lurch began discovering why German pilots who had fought Thunderbolts only at low altitude had fundamentally misunderstood the aircraft's capabilities. He climbed steadily, nursing the turbo-supercharger to operating temperature as altitude increased. Below 15,000 FT, the P-47 felt exactly as German combat pilots had described in their reports: heavy, sluggish in turns, unable to match German fighters in maneuverability. Theoretic climb was mediocre at best compared to the FW190 or Bf109. At this altitude range, any competent German pilot in a contemporary fighter could outmaneuver the Thunderbolt in sustained turning combat. But somewhere above 20,000 FT, the character of the aircraft transformed completely. The turbo-supercharger, driven by exhaust gases and becoming increasingly efficient as air pressure decreased with altitude, began forcing massive quantities of compressed air into the engine cylinders. While German engines gasped for oxygen and lost power as altitude increased, the R-2800 maintained full-rated power. At 25,000 FT, where German fighters were operating at perhaps 70% of their sea-level power, the Thunderbolt's engine was still producing full-rated output. Lurcher pushed the throttle forward at 25,000 FT and felt the Thunderbolt accelerate with surprising vigor for such a large aircraft. He rolled into a dive to test high-speed characteristics, and the aircraft responded with an enthusiasm that bordered on violence. The P-47 accelerated past 500 mph in a steep dive, reaching speeds where the controls stiffened dramatically as airflow compressed around the airframe. At this speed, recovery from the dive required both hands on the control stick and considerable physical strength. The aircraft was approaching the limits of compressibility that would not be fully understood until the jet age. The roll rate impressed Lurch immediately and contradicted everything German pilots had assumed about the heavy American fighter. Despite its size and weight, the Thunderbolt could roll faster than any German fighter Lurch had flown, including the FW190, which was considered excellent in roll performance. This characteristic, combined with its devastating dive speed, created a tactical advantage that German pilots had been reporting without fully understanding the implications. An American pilot in trouble at high altitude could simply roll inverted and dive away at speeds no German fighter could match. Any Luftwaffe pilot attempting pursuit would encounter compressibility effects that the P-47's stronger airframe and more effective controls handled more successfully. Lurcher flew the captured Thunderbolt through a comprehensive test program, exploring the flight envelope systematically according to standard recline evaluation procedures. His preliminary report contained observations that troubled Luftwaffe headquarters staff, who still believed German fighter designs were fundamentally superior. At altitudes above 25,000 FT, where aerial combat was increasingly occurring as Allied bomber formations flew higher to escape German flak, the P-47 Thunderbolt was not inferior to German fighters. It was superior in specific, crucial ways that negated German advantages in maneuverability and rate of climb. Over the following weeks, Recline's engineers subjected Beetle to exhaustive testing according to standard AirRob's stellar procedures. They photographed every component from multiple angles. They measured every dimension with precision instruments. They weighed each major component and assembly. They tested every mechanism under a range of conditions. The turbo-supercharger system received particular scrutiny, as this innovation represented the main distinction between American and German approaches to high-altitude performance. What they uncovered during their detailed analysis astonished engineers accustomed to resource-limited design principles. The Pratt Whitney R-2800 double wasp consisted of 18 cylinders, arranged in 2 rows of 9 around a central crankshaft. Total displacement measured 2,804.5 cubic inches, equal to 45.96 liters. For comparison, the BMW 801D displaced 2,560 cubic inches, or 41.88 liters. But displacement alone did not account for the large power gap between the two engines. The R-2800 featured forged aluminum pistons, sodium-cooled exhaust valves to withstand extreme heat, and a crankshaft forged from high-grade steel alloy, a material German metallurgists examined with professional envy, recognizing substances they could no longer procure in sufficient quantities. The quality of American materials and manufacturing precision left the German inspection team in awe. Every component displayed evidence of careful machining to tight tolerances. Surface finishes were uniformly smooth across all parts. The magnetos used materials that had become rare in Germany, while the spark plugs contained high-grade ceramics superior to their German counterparts. The fuel injection system operated with a precision the Germans associated with laboratory instruments, not combat aircraft expected to perform reliably in extreme conditions. Most revealingly, the entire engine showed no evidence of material substitution or quality compromises brought on by shortages. The Americans had constructed this engine exactly as designed, using all specified materials, without the desperate improvisations that had come to define late-war German production. The turbo-supercharger system demonstrated a level of engineering sophistication Germany had tried to develop, but never successfully mass-produced. Exhaust gases from all 18 cylinders were routed through manifolds and insulated pipes along each side of the fuselage to a turbine unit located beneath and behind the cockpit. This turbine, spinning at incredible speeds, drove a centrifugal compressor that forced extra air into the engine's supercharger. The system included an intercooler to reduce the air temperature, increasing density and preventing destructive detonation. Automatic regulators maintained boost pressure and turbine speed, requiring minimal pilot input beyond adjusting manifold pressure. German engineers understood the theory perfectly and had conducted experimental programs pursuing similar ideas. Yet, they had never succeeded in integrating such a system into mass-produced combat aircraft. Largely due to material shortages and manufacturing constraints plaguing German industry, by 1943, the turbo-supercharger demanded exotic, heat-resistant alloys for turbine blades capable of surviving extreme temperatures while rotating at immense speed. The control system required precision-built components, and the ducting depended on heat-resistant materials and airtight seals to operate efficiently. Every element had to function flawlessly under combat conditions, enduring vibration, temperature extremes, from 60 at altitude to over 200 degf near the engine, and potential battle damage. Americans had solved all these challenges and fitted the entire system as standard equipment on every P-47 built. The turbo-supercharger was not a prototype or a limited-run feature. It was simply how the airplane worked, installed in thousands of production aircraft. This routine use of advanced technology revealed an industrial capacity that German engineers found almost impossible to comprehend. German technical reports from the Rechlin evaluations noted that the turbo-supercharger system alone represented a degree of engineering advancement and manufacturing ability that exceeded Germany's production capability. The materials, precision machining, and quality control required to build such systems reliably, at scale, simply lay beyond what German industry could achieve in 1943, given strategic shortages, bombing damage, and the replacement of skilled labor with forced workers. The armament layout offered another striking example of American abundance and attention to engineering detail. The P-47D mounted 8 Browning M2.50 caliber machine guns, 4 in each wing. Most German fighters of the era carried a mixed armament, typically 4 machine guns and 2 20mm cannons, or 6 guns in earlier versions. The American decision to install 8 heavy machine guns was a deliberate choice to maximize firepower, even at the cost of added weight and complexity. Each gun was supplied from its own ammunition box built into the wing, each holding 425 rounds, a total of 3,400 rounds. For comparison, the FW-190A typically carried around 2,000 rounds for its machine guns and 500 rounds for its cannons. A P-47 pilot could fire all 8 guns continuously for about 20 seconds, with a combined rate of fire nearing 100 rounds per second. When the guns were properly harmonized to converge at a single point, the volume of fire was devastating to any target. German test firings of the captured Thunderbolts weapons confirmed their lethal effectiveness. The installation quality impressed German ordnance specialists. Each gun was mounted in an electrically heated compartment to prevent freezing at high altitudes, where temperatures could plunge below 60 degrees Celsius. Spent shells and belt links were channeled through ejection chutes under the wings, preventing damage or control interference. The entire system performed flawlessly during Rechlin testing, firing thousands of rounds without a single jam or feed failure. Even the ammunition demonstrated another layer of American industrial excellence. The 50 caliber rounds featured armor-piercing cores, reliable incendiary compounds, and predictable tracer elements. Testing revealed that American ammunition was consistently more dependable than its German equivalent, which had suffered from declining quality as key materials grew scarce. The Thunderbolts' armor protection demonstrated American willingness to accept significant weight penalties in exchange for pilot survivability, a philosophical difference from German design priorities. The cockpit was surrounded by heavy armor plate on multiple sides. The pilot sat in what American designers called an armored bathtub that provided protection from below and from behind. The windscreen incorporated thick, bulletproof glass capable of stopping machine gun rounds and resisting cannon shell fragments. Additional armor plates protected critical systems, including oil coolers and the vulnerable turbo-supercharger. Total armor weight exceeded 200 lb, roughly equivalent to the weight of adding 2 additional machine guns with ammunition. German fighters typically carried less comprehensive armor protection, prioritizing lighter weight and better performance while accepting higher pilot casualties as an unavoidable cost of combat operations. The design philosophy difference revealed itself clearly in maintenance accessibility. American designers had clearly anticipated that mechanics working in forward air bases would need to service aircraft quickly, possibly at night, possibly under adverse weather conditions, possibly while under threat of enemy attack. Every major component could be accessed through large panels secured with quick-release fasteners that required only simple tools. The massive engine could be changed in the field within a few hours using standard hoisting equipment and following clearly documented procedures. German fighters designed with the expectation of factory-level maintenance for major repairs, typically required more extensive disassembly for major component service. This difference reflected American abundance versus German scarcity. The Americans could afford to dedicate engineering resources to maintainability because their industrial capacity allowed them to optimize designs for operational efficiency rather than pure production efficiency. The radio installation in the captured P-47 represented another area where American technology exceeded German equivalents. The aircraft carried an SCR-274N command radio for air-to-air and air-to-ground communication, plus an SCR-515A liaison radio, providing additional communication channels. Both units operated with a clarity and range that exceeded contemporary German radio capabilities. German radio systems suffered from persistent interference problems that American engineers had apparently solved through superior component design and better shielding. The radios also integrated with an identification friend or foe system that automatically identified friendly aircraft to ground controllers, preventing friendly fire incidents. This level of automated identification represented a sophistication that German forces lacked in 1943. Perhaps the most profound revelation for German engineers came not from any single advanced system, but from the cumulative impression of quality and completeness throughout the aircraft. Every component appeared to be the best possible version of that component that American engineers could design and manufacturers could produce. Nothing was obviously compromised due to material shortages. Nothing showed clear evidence of substitute materials being used because preferred materials were unavailable. Nothing reflected the desperate improvisations that increasingly characterized German late-war production as strategic bombing degraded industrial capacity and material shortages became acute. German technical reports compiled at Reclean and distributed through the Luftwaffe technical services emphasized this point repeatedly. The P-47 Thunderbolt had been built exactly as the designers intended, using all specified materials and processes with no apparent compromises forced by resource scarcity. This level of manufacturing fidelity to original design specifications was becoming increasingly difficult for German industry to achieve as the war progressed. The flight testing program continued through the winter of 1943 and into early 1944 as additional P-47s were captured and brought to Rechlin for comparative evaluation. On May 29, 1944, another P-47 landed in German hands when 2nd Lieutenant Lloyd S. Hathcock of the 3001st Fighter Squadron, 332nd Fighter Group, became disoriented during a ferry flight and mistakenly landed at the enemy-held Rome Littorio airfield in Italy. His aircraft, serial number 4275971, was quickly seized by German forces. This P-47 had previously been the personal mount of George Nowotny, an 8 Victory Ace flying with the 317th Fighter Squadron. The Germans transferred the aircraft to Wrestling, where it was initially designated 8+6, then later transferred to Zircus Rosarius on October 12, 1944, where it received the designation T9+LK. The testing data accumulated at Recline produced tactical recommendations that were compiled and distributed to frontline Luftwaffe fighter units. These recommendations advised that engaging P-47s below 15,000 FT offered the best probability of success for German pilots, as the Thunderbolt's poor low-altitude performance and slow rate of climb gave German fighters clear advantages in that regime. Pilots were specifically warned to avoid diving away from attacking Thunderbolts, as the American fighter would simply accelerate to speeds that German aircraft could not match in a dive. The reports emphasized that damaged P-47s frequently continued flying, despite battle damage that would destroy German fighters, so attacks needed to be pressed home aggressively with concentrated fire rather than assuming that a few hits would down the aircraft. But the tactical advice, however useful to individual pilots, could not address the fundamental strategic problem that became increasingly apparent. Germany was fighting an opponent with effectively unlimited material resources relative to German industrial capacity. Every damaged or destroyed P-47 was replaced within days from production that exceeded 300 aircraft per month at peak output. American pilot training programs produced skilled aviators in quantities Germany could no longer match as training was compressed and fuel shortages limited flight hours. The logistics system supporting American Thunderbolt operations delivered fuel, ammunition, and spare parts without apparent constraint, while German logistics deteriorated under relentless Allied air attack. The captured P-47s were eventually transferred to the Wunderschuss Rosarius, the special Luftwaffe demonstration unit commanded by Flugkapitän Theodor Rosarius. This specialized unit traveled to frontline fighter bases throughout occupied Europe, allowing German pilots to see captured Allied aircraft firsthand and learn recognition features and combat characteristics. The demonstrations served dual purposes, both educational and psychological. Pilots learned the visual recognition features and tactical characteristics of enemy aircraft they would face in combat. But they also saw physical evidence that Allied equipment was often superior to their own in specific important capabilities, particularly at the high altitudes where combat increasingly occurred. Post-war interviews with Luftwaffe pilots who attended these demonstrations revealed the psychological impact of seeing the captured American fighters' capabilities demonstrated directly, while the Circus Rosarius pilots could show that German fighters maintained advantages in certain flight regimes, particularly at medium altitudes. The demonstrations made clear that at the altitudes where American bomber formations operated, escorted by P-47s and later P-51s, German fighters were at a distinct disadvantage. The intelligence gathered from captured P-47s included detailed performance data that directly contradicted some of the optimistic assumptions that had circulated in Luftwaffe briefings earlier in the war. At sea level, the P-47D achieved a maximum speed of approximately 350 mph, not particularly impressive compared to the FW-1D-90A's 408 mph at the same altitude. At 10,000 ft, the Thunderbolt reached approximately 375 mph, but at $30,000 ft, the P-47 achieved 426 mph, while the Focke-Wulf struggled to reach 370 mph, and the Bf-109G managed approximately 300 mph, 85 mph, or the performance advantage at combat. Altitudes was clear, decisive, and growing more important as Allied bomber formations flew higher to escape German anti-aircraft fire. The service ceiling comparison proved equally discouraging for German pilots. The P-47 Thunderbolt service ceiling reached 42,000 meters. FT German fighters rarely operated effectively above 35,000 FT, and their performance degraded rapidly at higher altitudes due to reduced engine power in the thin air. American bomber formations could and did operate at altitudes where German interceptors could barely reach them, and where the interceptors that did reach combat altitude had insufficient power, reserves for effective combat maneuvering. The P-47 escorts operated comfortably at these altitudes, maintaining full combat capability while German fighters struggled. Range comparisons between American and German fighters revealed another dimension of American industrial and logistical superiority. With external fuel tanks, the P-47D could escort bombers on missions penetrating deep into Germany. Early P-47 models had limited range that restricted their effectiveness, but by 1944, Thunderbolts equipped with 108 drop tanks routinely flew missions covering 1,000 meters or more. German fighters designed primarily for short-range interception. Missions in defense of the Reich lacked the internal fuel capacity for extended operations. The difference in operational radius meant that American fighters could engage at times and places of their choosing, while German fighters were forced to fight defensively. The captured Thunderbolts also provided insights into American pilot training and tactical doctrine through examination of gun camera footage and analysis of combat damage patterns on aircraft that had survived combat before capture. The evidence suggested that American pilots consistently employed tactics that emphasized the P-47's strengths while avoiding situations that exposed its weaknesses. They maintained high altitude where the turbo-supercharger provided clear advantage. They used dive and zoom attacks rather than attempting sustained turning dogfights, where German fighters held advantage. They worked in coordinated pairs or four-ship flights rather than engaging in individual combat, maintaining mutual support even when this meant declining apparently advantageous individual engagement opportunities. The discipline evident in American tactical execution impressed Luftwaffe analysts who studied the evidence. Many Luftwaffe pilots, particularly experienced aces, preferred to fight individually, relying on personal skill and aggressive tactics to achieve victory. American pilots appeared to follow established doctrine consistently, supporting each other systematically, and rarely allowing individual pride or aggression to override tactical sense. This disciplined approach, combined with superior, high-altitude equipment and growing numerical advantage, created a combination that even veteran German pilots found increasingly difficult to overcome as the war progressed. By D-Day in June 1944, the strategic situation had deteriorated to the point where intelligence on captured aircraft provided little practical value to Germany's war effort. The Luftwaffe understood clearly that American equipment was superior in important ways. They comprehended American tactics. They had detailed technical data on Allied aircraft performance. But this knowledge could not produce the resources, strategic materials, manufacturing capacity, and trained personnel needed to effectively compete. The Recline reports, carefully compiled and professionally distributed throughout the Luftwaffe technical services, served primarily to document the technological and industrial gap that was driving Germany toward inevitable defeat. The comparison between American and German engine production illustrated the impossible position Germany faced. Pratt Whitney, along with Leon C. Ford Motor Company, produced over 125,000 R-2800 engines by war's end. Production of this single engine type exceeded Germany's entire combat aircraft engine production. BMW produced approximately 61,000 examples of the 801 radial engine throughout the entire war. The Daimler-Benz DB605, Germany's most produced inline engine, reached approximately 42,400 units total production. American production of one advanced engine type surpassed Germany's total output of all combat aircraft engines combined. American industry in 1944 produced approximately 96,000 aircraft, while Germany reached approximately 25,000 aircraft of all types. The United States produced 38,000 fighters alone, plus 16,000 heavy bombers, plus thousands of medium bombers, transports, and trainers. When combined with British and Soviet production, the Allied advantage in aircraft production exceeded 5.1 by 1944. The industrial base supporting this production operated on a scale Germany could not match. The Aluminum Company of America alone produced more aluminum than Germany's entire aluminum industry. Individual American steel plants frequently outproduced the entire Ruhr industrial region. The automotive factories that manufactured vehicles operated on moving assembly lines where German plants used batch production methods. Even the machine tools that built the machines that built the aircraft were themselves produced in quantities that allowed American industry to supply not only its own requirements, but also substantial quantities to British and Soviet allies. The captured P-47s ultimately ended their service in the chaotic final months of the European War. The aircraft, designated T-9 plus FK, originally William Roach's Beetle, was recovered by American forces at Göttingen in May 1945, found among a collection of captured Allied aircraft that the Germans had been evaluating. Photographs taken by American forces show the aircraft still wearing partial German markings parked alongside FW-190 and Bf-109s in what was effectively a museum of captured equipment, documenting the breadth of the Luftwaffe's intelligence-gathering effort. The Thunderbolts that served with German evaluation units provided German pilots and engineers with an education they desperately needed, but had received too late to matter strategically. The aircraft demonstrated that American industrial philosophy prioritized absolute capability over elegant efficiency, abundant resources over careful optimization, and systematic material advantage over individual technical excellence. These priorities, when implemented with nearly unlimited resources and manufacturing capacity, produced weapons systems that outclassed German equivalents in the aggregate, even when German designs showed superior characteristics in specific, isolated parameters. The lesson extended far beyond the P-47 itself. Every category of captured American equipment told the same fundamental story. The B-17 Flying Fortress bomber, with its quartet of turbo-supercharged Wright Cyclone engines, represented a strategic bombing capability Germany never achieved. The P-51 Mustang, combining American airframe engineering with the British Rolls-Royce Merlin engine, created what many historians consider the finest piston engine fighter of the entire war. The P-38 Lightning, with its twin turbo-supercharged engines and tricycle landing gear, demonstrated American willingness to pursue unconventional solutions. Each aircraft type revealed the same fundamental American approach: solve problems through superior engineering, supported by unlimited industrial capacity rather than through clever optimization constrained by resource scarcity. Luftwaffe analysts clearly observed that they were not being defeated by superior tactics or better-trained pilots. Though American training programs were producing adequate pilots in overwhelming numbers, they were being defeated by an industrial system that could design adequate equipment and then produce it in quantities that rendered German qualitative advantages increasingly irrelevant. The Americans designed to their industrial strengths, leveraging massive manufacturing capacity, abundant raw materials, and efficient logistics. Germany, by 1943, was designing despite crippling industrial limitations, attempting to achieve through engineering cleverness what they could no longer accomplish through industrial might. The strategic implications were well documented throughout the Luftwaffe's technical services. By the end of 1943, Germany had entered the war with arguably the world's most advanced air force, equipped with aircraft that were generally superior to their opponents' ONA 1-1 bases. German pilots were better trained than most opponents initially. German tactics were more refined, but German industry fundamentally lacked the capacity to sustain these advantages when facing opponents with vastly greater industrial resources. American aircraft production doubled repeatedly. In 1940, again in 1941, again in 1942, and continued expanding until by 1944, American factories were producing over 96,000 aircraft annually, while Germany never exceeded 40,000 aircraft in any year. Despite desperate efforts to increase production, the quality gap between American and German aircraft widened steadily, rather than narrowing. In 1942, German aircraft were often superior to their American opponents. By 1944, American aircraft equaled or exceeded German designs in virtually every important category. By 1945, the gap had become a chasm. American fighters like the P-51H and P-47N represented evolutionary refinement of already excellent basic designs. German fighters like the TR-152 represented desperate attempts to extract more performance from industrial systems, collapsing under the combined weight of strategic bombing, raw material shortages, and the replacement of skilled workers with poorly trained forced labor. The psychological impact on Luftwaffe morale of facing endless streams of capable enemy aircraft proved as destructive as the material losses. German pilots reported feeling less like warriors in honorable combat and more like targets in a systematic destruction campaign. No matter how many Allied aircraft they shot down, more appeared the next day. No matter how skillfully they fought, American numerical superiority eventually prevailed through sheer attrition. The knowledge that their opponent's equipment was often superior to their own, delivered in far greater quantities, supported by better logistics, and flown by adequately trained pilots who were quickly replaced when lost, created a pervasive sense of inevitable defeat that spread throughout the fighter forces during 1944. The captured P-47s served as tangible physical evidence of this reality. These were not propaganda claims or exaggerated intelligence reports. They were actual aircraft that German pilots could examine directly. The Thunderbolt was not some miracle weapon or revolutionary technological breakthrough. It was simply a very good fighter aircraft, properly designed for its mission, adequately powered, well-armed, appropriately protected, and manufactured in quantities sufficient to overwhelm opposition through systematic application of material superiority. The final historical irony was that the Germans learned these lessons thoroughly, documented them professionally, and grasped the implications completely, yet could never apply the knowledge they gained. Understanding American industrial superiority did not grant Germany the aluminum, steel, fuel, skilled labor, undamaged factories, and functioning transportation networks needed to produce equivalent aircraft in equivalent quantities. Knowing the P-47's exact capabilities did not provide the high-temperature alloys, precision manufacturing equipment, quality control systems, and trained workforce needed to build comparable turbo-supercharger systems. Intelligence gathered from captured aircraft documented the dimensions of German defeat with professional thoroughness, without offering any realistic path to avoid that defeat. When Allied forces captured Rechlin and its associated facilities in May 1945, they found extensive documentation of the captured aircraft evaluation program. German technical reports filled filing cabinets detailing every measurable characteristic of every American and British aircraft that had been examined during the war. Their reports were models of technical thoroughness and scientific objectivity. They also represented thousands of man-hours spent meticulously documenting capabilities that Germany could observe and measure, but never replicate given their deteriorating industrial situation. American technical intelligence teams who reviewed the German reports after the war noted with professional interest that German engineers had understood American aircraft capabilities more clearly and in greater detail than American commanders sometimes did. The Germans had identified weaknesses in American designs that American pilots learned to work around through experience. The technical analysis was frequently more detailed and rigorous than equivalent American evaluations of their own equipment. German engineering competence had never been in question, but the American reviewers also noted what the German reports implicitly revealed about Germany's strategic situation. Germany had attempted to fight a modern industrial war with an industrial base insufficient for the task. They had compensated through excellent engineering, superior pilot training in the early war years, and tactical innovation born of necessity. These advantages had sustained them through early victories against opponents with similar resource constraints, but against an opponent like the United States, possessing industrial capacity that exceeded all other major powers combined. Excellent engineering and tactical skill could only delay the inevitable outcome rather than change it. The story of German engineers examining captured P-47 Thunderbolts provides a clear case study in the realities of industrial warfare as it had evolved by the Second World War. The Thunderbolt succeeded not because it was the absolute best possible fighter aircraft by every conceivable measure, but because it was a very effective fighter aircraft produced in quantities that made isolated examples of technical superiority strategically irrelevant. American industry built 15 683 Thunderbolts, while simultaneously building 15,486 P-51 Mustangs, 10-37-38 Lightnings, 13,738 F-6F Hellcats, and 12,571 F-4U Corsairs. Total American fighter production exceeded 70,000 aircraft during the war. And each aircraft represented thousands of hours of skilled labor, tons of aluminum and steel, hundreds of precision components and manufacturing capacity that Germany could not approach. The P-47 Thunderbolt became a symbol of American industrial dominance to German pilots who fought against it. Luftwaffe pilots used the same nickname American pilots had coined, calling it the Jug in acknowledgement of its ungainly appearance. They also called it Indiana after the Thunderbird emblem many squadrons painted on engine cowlings. As losses mounted and the strategic situation deteriorated, some referred to it simply as that 8-gun fighter and learned through bitter experience to avoid engaging Thunderbolts at altitudes where the American fighter held tactical advantage, which increasingly meant avoiding combat above 20,000 ft. where the turbo-supercharger gave the P-47 decisive performance superiority. By the war's end, P-47 Thunderbolts had destroyed approximately 3,752 enemy aircraft in aerial combat, while approximately 3,499 P-47s were lost to all causes, including operational accidents, mechanical failures, and ground attack missions. This roughly 1.1 exchange rate in total losses appears unremarkable, until one considers that Thunderbolt served primarily in the ground attack role from mid-1944 onward, facing intense anti-aircraft fire during low-level missions rather than engaging primarily in air-to-air combat. In the pure fighter escort role during 1943 and early 1944, P-47s achieved significantly better exchange rates, particularly at high altitudes, where the turbo-supercharger advantage was most pronounced. The ground attack role revealed yet another dimension of American design philosophy that emphasized versatility. When P-51 Mustangs, with their superior range, began taking over bomber escort duties in 1944, the 9th Air Force reassigned many Thunderbolt groups to tactical air support missions. The rugged P-47, with its reliable air-cooled radial engine and heavy armor protection, proved exceptionally well-suited for dangerous, low-altitude attack missions, the same characteristics that made it seem ponderous in low-altitude dogfights. Substantial size, heavy weight, comprehensive armor, powerful armorament made it nearly ideal for ground attack missions where survivability and firepower mattered more than maneuverability. Thunderbolt pilots flying ground attack. Missions destroyed staggering quantities of German military equipment. Official claims documented through gun camera footage and after-action reports included over 86,000 railway cars, 9,000 locomotives, 6,000 armored fighting vehicles, and 68,000 trucks destroyed or damaged. While such claims inevitably included some duplication, the scale of destruction was undeniable and had measurable impact on German military operations. The P-47, armed with bombs and rockets in addition to its 8 machine guns, had evolved into a true multi-role combat aircraft. German ground forces learned to recognize and fear the characteristic sound of Pratt and Whitney R-2800 radial engines at low altitude. The deep rumble provided warning of impending attacks that German troops were largely helpless to prevent. The psychological impact of constant air attack, combined with substantial material losses and the disruption of logistics and communications, measurably degraded German ground forces' combat effectiveness throughout 1944 and 1945. The question of what ultimately happened to the captured aircraft serves as an epilogue to this account. William Roach's P-47D Beetle 42-22-490, designated T9+FK by the Germans, survived the conflict and was recovered by American forces at Göttingen in May 1945. After being evaluated by American intelligence teams studying German testing methods, the plane was eventually dismantled and scrapped. Lloyd Hathcock's P-47D 42-75971 marked T9+LK at a similar end, retrieved but not preserved for posterity. The pilot's fates after capture, however, differed dramatically. William Roach spent the rest of the war at Stalag Luftwaffe in Barth, Germany. He was freed by Soviet troops in May 1945 and returned home to the United States. Lloyd Hathcock spent 11 months as a prisoner of war, primarily at Stalag Luftwaffe, the site of the famous Great Escape, which had occurred just 3 months before his arrival. He was the only African-American pilot among thousands of white prisoners at the camp. When Soviet forces advanced westward in January 1945, German guards evacuated the camp, forcing prisoners on a harsh winter march to Stalag 70A and later Stalag 13D. Hathcock was liberated by Allied troops in April 1945. After returning to the United States, Hathcock played an important role in the post-war desegregation of the U.S. Air Force. He later pioneered advancements in aerial reconnaissance photography at Wright-Patterson Air Force Base, Hans Werner. Lurcha survived the war despite flying over 125 different aircraft types, including numerous captured Allied planes throughout the conflict. His exceptional safety record, never crashing or seriously damaging an aircraft, remains unparalleled in aviation history. Following the war, Lurcha provided extensive debriefings to Allied intelligence about German aircraft research and development programs. His memoirs, published in 1977 in German and translated into English in 1980, remain one of the most comprehensive, first-hand accounts of Germany's captured aircraft, testing and provide valuable insight into how the Luftwaffe evaluated Allied aviation technology. The broader lesson emerging from the saga of the captured P-47 Thunderbolts in German hands goes beyond the technical details of a single aircraft type. The Thunderbolt trials at Rechlin illustrated that by 1943, the fate of the air war over Europe was being determined not by pilot skill, tactical creativity, or even aircraft performance in narrow technical terms, but by industrial capacity applied at national scale. The nation capable of producing adequate equipment in overwhelming quantities, while simultaneously building everything else a modern military required, would inevitably triumph over adversaries with technically superior weapons built in insufficient numbers. By late 1943, Germany was a nation trying to compete industrially against opponents whose combined manufacturing power exceeded its own by factors of 5 or more. When Britain refused to surrender after France's fall, when the Soviet Union endured the initial German onslaught and relocated its industry beyond German reach, and when the United States entered the war with its vast, untouched industrial base, Germany's chance at military victory had effectively vanished. The only question left was how long Germany could continue fighting, and how much devastation would unfold. Before the inevitable conclusion, the story of Beetle and the other captured Thunderbolts at Rechlin thus becomes a microcosm of Germany's larger strategic predicament. German engineers could study American aircraft, comprehend American technological capabilities, and accurately evaluate U.S. industrial strength. This data was meticulously gathered, analyzed, and recorded. But knowledge alone could not create the aluminum, steel, rubber, fuel, machine tools, skilled labor, intact factories, and functioning railways required to match American production. The Republic P-47 Thunderbolt, examined in painstaking detail by German engineers at Rechlin, revealed a fundamental truth about industrialized warfare in the 20th century. Material abundance, systematically applied through sound engineering and efficient tactical use, would always defeat technical excellence limited by resource shortages. The most formidable weapon in America's arsenal was not any single machine, but the entire industrial system capable of conceiving, designing, developing, testing, producing, and sustaining thousands of complex weapons simultaneously, while maintaining quality and continuously improving. Through combat experience, the captured Thunderbolts conveyed this lesson with undeniable clarity. German engineers measured it precisely, recorded it professionally, and reported it accurately through their command channels. But the insight arrived too late to change history. By the time William Roach's Beetle was being carefully inspected at Rechlin in late 1943, the war's outcome had already been sealed by industrial mathematics that no level of German engineering skill or pilot valor could overcome. The Thunderbolts sitting on German airfields, bearing hastily painted Balkenkreuz insignia over American stars, symbolized a future already realized, one in which industrial capacity had become the decisive factor in modern warfare.